The next essential way to implement climate smart farming we will discuss is improving natural resources by improving soil health. Improving natural resources means improving the four ecosystem processes: water cycle, mineral cycle, biological communities, and energy flow. The four ecosystem processes are interconnected. When you improve one, you improve them all. For example, when you increase organic matter and improve mineral cycling, you improve the water cycle by improving infiltration and retention of water. The four main ways to improve soil health for the climate smart farm is to increase organic matter, improve soil structure by disturbing less, keep soils covered, and keep plants growing throughout the year. Improving soil health can help plants deal with more extreme weather, including higher temperatures, periods of high rainfall, and periods of drought. I'll discuss how certain soil health practices help with climate resiliency and ways to implement them on the land. Improving each one of these is going to have multiple benefits to the climate resilient farm. Soil organic matter is so important for buffering changes in weather. For example, it is estimated that soil containing 1% of organic matter can hold as much as 20,000 gallons of water per acre. This is especially crucial during periods of low rainfall. During periods of high rainfall, more soil organic matter and better soil structure can improve drainage and reduce runoff and erosion. NRCS's revised universal soil loss equation accounts for organic matter's stabilizing effect by reducing its factor of erosion by 20 to 33% for each 2% increase in organic matter. In addition to the water cycle benefits, soil organic matter improves biological communities in the soil, which improves the mineral cycle. The organic matter provides a food source to living organisms underground. These living organisms, both large and small, cycle nutrients, making them available to plants. When you increase soil organic matter, you improve the soil's cation exchange capacity. This improves the soil's ability to hold nutrients and prevent leaching. You can increase soil organic matter in three main ways. The first is through roots, especially herbaceous roots. For example, approximately 1/3 to 1/2 of grass roots die each year, leaving channels of organic matter where the roots once were. Air and water can occupy this space as the dead roots break down. This is a significant and effective way to increase organic matter, especially deeper into the soil profile. Another way to increase organic matter is to top dress soil with manure or plant residues. Biological organisms will break down this material and pull it down into the soil. Manure can also be injected into the ground. If you look at the picture on the right, you can see how organic matter is distributed through the soil profile. It is darker on top, and then the soil gradually becomes redder as the organic matter content decreases and the color of the soil mineral comes through. A third and important way to maintain organic matter in the soil is to disturb it less or not at all. Tillage slices and dices soil aggregates, creating more surface area for biological activity and speeding the breakdown of organic matter. While some biological activity in the soil is good, too much causes organic matter to convert to carbon dioxide gas that escapes into the air. Roots, soil amendments of carbon sources such as manure, and tilling less or not at all are all methods to maintain or increase your soil organic matter. Soil organic matter can have a measurable effect on crops in times of drought. A 2021 study found that counties in the US with higher soil organic matter are associated with greater yields, lower yield losses, and lower rates of crop insurance payouts under drought. During severe drought, an increase of just 1% of organic matter was associated with a corn yield increase of 32.7 bushels per acre and a 36% reduction in the mean proportion of liabilities paid. One of the most difficult aspects of climate change we deal with in the Northeast is the increased rainfall amounts and the increased frequency of heavy rainstorms. This is defined as a storm with over 2 inches of rain in a 24-hour period. This much rain can cause erosion, runoff, leaching of nutrients, flooding, and ponding in farm fields. A solution for dealing with heavy rain is the same as that for improving soil organic matter. Disturb the soil less or not at all, and reduce compaction with living roots and biological communities. The method that has the biggest impact is no-till. If no-till can't be accomplished, then the goal could be to disturb the soil less through methods such as reduced till, shallow till, zone till, ridge till, and what some farmers call strategic till when tillage is only used to address a problem. Let's look at how biological communities and roots improve drainage. Compare these two soils. These are the same soil type but different management, untilled versus tilled. The soil on the left was in a no-till permanent pasture, and the soil on the right was in a continuous till crop field. What do you notice about the soil on the left? Look at the soil texture. Even though it is the same soil, the texture appears completely different. The soil on the left has a lumpy, cottage cheese-like consistency, while the consistency of the soil on the right is very fine, like it has been sifted. The clumps on the left are formed by living organisms in the soil that excrete glues which hold the soil together. Only by not disturbing the soil will these soil microorganisms survive. The soil on the right, which has fewer biological organisms, will tend to dissolve in water. We can see illustrated in this picture how different management regimes from reduced till, multiple till, and no-till fields and what happens when they are placed in a cylinder of water. The clods that have been tilled most frequently dissolve in water. That is because they lack biological organisms and the glues they secrete to hold the soil together. Soil organisms such as earthworms also create pathways through the soil that can hold air and water. The photo on the left shows a rubber mold that was taken of nightcrawler channels in a crop field. Water seeps into these channels instead of running off the field or ponding on top. Worms and other invertebrates also play a part in adding organic matter to the soil profile. They can take dead plant matter from the soil surface and pull it down into the soil to digest. The gentle tilling mixes the soil layers without introducing too much oxygen and thereby preserves carbon in the soil. The photo on the right shows dye that was applied to the surface of a pasture soil and how it infiltrates through the channels made by roots and soil organisms. Compaction is a biological problem needing a biological solution. By increasing organic matter and maintaining channels in soil made from roots and living organisms, infiltration can increase. The next problem we'll discuss is increased soil temperatures. Soil temperature affects plant growth in a number of ways. High soil temperature can discourage or kill beneficial organisms. It can reduce root growth and nutrient uptake, which affects yield. High temperatures also increase soil evaporation, so more water is lost. Temperature has an effect on what lives in the soil. For microorganisms such as nitrogen-fixing bacteria and mycorrhizal fungi, ideal soil temperatures range from 50 to 96 degrees Fahrenheit. For macroorganisms such as worms or arthropods, the ideal temperature is lower, around 50 to 75 degrees Fahrenheit. Also, the warmer the soil, the more biological activity and the more soil organic matter is reduced to carbon dioxide. For this reason, warmer soils have a harder time accumulating organic matter than cooler soils. In most plants, the ideal soil temperature range for growth and nitrification is 65 to 86 degrees Fahrenheit. As soil temperatures get hotter, plant growth slows and diminishes. This illustration shows root shrinkage of potatoes based on soil temperature. In cool season grasses, growth stops above 90 degrees Fahrenheit. In corn, it is about 95 degrees Fahrenheit. Soil temperature also affects evaporation. The hotter the soils, the more water is lost. Evaporation depends on soil temperature, sun, wind, and humidity, but on average in the Northeast, evaporation increases 1% with each degree increase in soil temperature. At 68 degrees Fahrenheit, almost all of the water in the soil is available for plant growth. When the soil temperature increases to 98 degrees Fahrenheit, the evaporation rate is 30% higher. Water evaporates from soil until a dry layer is formed and then evaporation decreases. Cover can greatly influence soil temperature. On this warm, sunny, dry day early in the growing season, there was a 45-degree difference in soil temperature at 1-inch depth due to different soil covers. A solution to keeping soil temperatures moderate and maintaining ideal soil moisture levels is to cover the soil with plants or mulch. This photo shows a no-till organic farm that adds straw between the rows and around the vegetable plants. Because the soil is covered, it loses a lot less moisture. In fact, this vegetable farm in upstate New York doesn't use irrigation as much except during seed starting and transplant time. In this photo, we see that the farmer left a thick residue of chopped corn stalks and soybeans were planted into it. Both scenarios, the added straw in the example in the previous slide and the crop residue in this slide, help increase or maintain organic matter in addition to buffering soil temperatures. Soil surfaces can also be covered with living plants in the form of cover crops. Cover crops have all the same advantage as dead plant material, but also have the added benefit of causing fields to be drier in spring and retain more moisture in summer by shading soil and keeping it covered. Cover crops moderate moisture in fields and captures more energy and provides living roots for longer in the growing season. Cover crops extend the amount of time over a year that sunlight is captured, converting it into energy and stored in the soil. A cash crop may only convert sunlight 4 to 5 months out of the year. A cover crop that is grown before or after the cash crop season can extend the length of time that sunlight is utilized. Plants are like solar panels. They capture sunlight and convert it to energy. Soil is like the battery and stores that energy in the form of roots, biological organisms, and other organic matter. The longer that there are living roots growing, the more energy gets put into the soil. This farmer planted a winter cereal rye after corn harvest in the fall. You can see that in the spring, the winter rye is green and growing before the trees have leafed out. It is capturing solar energy in a field that would have otherwise been bare soil and not able to capture solar energy, put it into the ground. This farmer planted a diverse mix of summer annuals on a field which had been left fallow in his crop rotation. He is roller crimping it to terminate the cover crop. He will plant a fall crop into the residue. The cover crop residue serves as mulch for the cash crop. Farmers with a longer growing season have more opportunities for cover crops. In the Northeast, cover crops have been somewhat challenging, especially in more northern areas. However, in recent years, first and last killing frosts are happening later in the fall and earlier in spring. This means a longer window of time for cover crops to get established and grow. Farmers that can't start planting earlier because their fields are too wet to work will find them drier and less susceptible to compaction with cover crops. A longer growing season makes a big difference when it comes to the success of a cover crop. These photos show the growth on December 1st of 3 different seedings of winter rye at the NRCS Plant Materials Center in Big Flats, New York, which is in a hardiness zone of 6A. You can see that an earlier planting nets significantly more biomass than plantings a month later. Because we are challenged with the length of growing season in the Northeast, it may take some creative thinking and planning to get cover crops to work. For example, a farmer may need to go to a shorter day corn or soybeans and follow that with a triticale crop that they can harvest for forage as shown in the picture on the left, or an interseeding of red clover with wheat as shown in the picture in the middle, or plant summer annuals in a fallow field as shown in the picture on the right. In colder areas of the Northeast, such as hardiness zones 4 or lower, cover crops can be especially challenging. Some successful strategies have included using winter rye or other cereals. Legumes planted for only part of a season will probably not have enough time to fully grow and may not be successful. Crop planning is very important. Fields that have early crops such as garlic, lettuce, or brassicas can be harvested in midsummer, then planted to a cover crop. The cover crop will continue to grow the next spring and be terminated in midsummer so that the land can be planted to a fall crop. Other strategies include interseeding, for example, red clover and wheat, or hairy vetch with corn. Fields that are fallow for a year can be planted to fast-growing summer annuals. For more information and to sign up for the Northeast Climate Hub's quarterly newsletter, please visit our website.